dear students. We are living still in chapter 2. For today, we're going to talk about section 2. Okay? In our prior lectures, we've talked about how to write the dissociation reaction for the ionic compounds and how to write the ionization reaction for the molecular electrolyte compounds. So maybe you think why we studied those things. Okay, today you will know why we learned them, because of in the colligative property we will need them in some steps. Okay, about the colligative properties, we have 4 properties which are vapor pressure lowering or lowering vapor pressure, freezing point depression, boiling point elevation, and osmotic pressure. So these are 4 colligative properties. They are depending on the concentration of the solid rather than their identity, or instead of their identity or their nature. So the word of colligative property came from a Latin word colligatus. It means the collecting numbers of a solid. Very well. We will talk about each of them one by one. But for now, it's very important to know that freezing point depression, we have delta TF as a symbol of freezing point depression, and we have delta TB as a symbol of boiling point elevation. We will study that to one mathematically. Okay, we have some mathematical problem and we're going to solve them. But the first one and the last one, we will talk about them just theoretically. I mean, we're going to explaining them and showing something. And after that, we'll be finished. Okay, let's start by the colligative properties for today. Why we called colligative properties? Why we call them colligative properties? Because of they are increasing with increasing the concentration of the solid, and they will decrease with decreasing the concentration of the solid. Look, what I mean about that. Okay. Chapter 2. Okay. Let's see. When I mention vapor pressure lowering, I mean lowering in vapor pressure, not only vapor pressure, okay? If we increase the concentration of the solid, so we will have more lowering in vapor pressure, not increasing vapor pressure, okay? Don't confuse. Look. If we increase the concentration of the solute, we will see more lowering in vapor pressure. We will see more lowering in vapor pressure. If we increase the concentration of the solute, we will have more depression, more decreasing in the freezing point. If we increase the concentration of the solute, we will have more elevation of the boiling point and more increasing elevation of osmotic pressure. So 2 of them will be increased with increasing the concentration of the solid, and the first 2 ones will decrease, will increase with increasing the concentration of solid, but in terms of decreasing. What I mean, it means we have lowering in vapor pressure. If we increase the solute, we will have more lowering. We have depression in freezing point. If we increase the concentration of the solute, we will have more depression. About the boiling point elevation, we will have more boiling point elevation and we will have more osmotic pressure. So that's about the vapor pressure. Okay, when we say vapor pressure, I mean lowering in vapor pressure, not only vapor pressure, lowering in vapor pressure. We will have more lowering in vapor pressure, not more vapor pressure, more lowering in vapor pressure. Well, The first colligative property is vapor pressure lowering. Let's see what is the vapor pressure. First of all, I prefer to explain the vapor pressure in here. Okay, suppose that we have a beaker, okay, and let's put some amount of solvent, whatever, any solvent. This is some solvent. And we should close the cup of the beaker. So this is the cup of beaker. I close it. Okay, the cup is closed. And now let's heat it up. We have to put some fire from the bottom of the beaker. And what will be your observation? We can see that the temperature starting to be raised, and then the molecules of the solvent begin to vaporization. Okay, now we have more molecule of the solvent, so we will have more vapor pressure. We will have more vapor. This is vapor. Okay, we have more molecule of the solvent, so we will have more vapor. This is vapor. And if we continue heating the solvent, so it will be vaporized continuously until in here we have enough pressure, we have more vapor, so it cannot be vaporized anymore. So in that case, for example, 10 molecules of the solvent will be a new vapor. So in contrast, in this vapor, 10 molecules become a liquid again. So there will be an equilibrium between the vapor and the liquid, gas and liquid. Okay, so the first step, we're going to heat the beaker, and then the liquid begins to vaporization, and the vapor molecules in here will be increased until in here we will have enough pressure that cannot receive more vapor. That's why in that case, the amount of a new vapor, okay, we will have some new molecules as a vapor. So in contrast, same molecules become a liquid. So there will be an equilibrium between gas and liquid. So that equilibrium called vapor pressure of a liquid. So just by looking the name of the vapor pressure, we can have a little idea about the vapor pressure. It means pressure of the vapor. Pressure of the vapor. Okay, it's the pressure caused by a molecule in the gas phase that are in equilibrium with the liquid phase. Let's see why if we add some solute to a pure solvent, the vapor pressure lowers. Why? How we can see or how we can discuss this phenomena. Again, I'll do something for you, and it helps you for understanding about that. It's very good. Look, again, we have the same beaker, but in this case, we don't have pure solvent. We will add some solute. So what will be your expectation? Well, adding solute into pure solvent, because of vapor pressure is a colligative property, so there will be lowering in the vapor pressure. You see now, look, this is pure solvent molecules. It's pure solvent molecules. Now, let's add the second molecule as a molecule or molecules of a solute. So the black colors are molecules of a solute. Again, close the container. Now, let's heat the solution. Look, in here, the amount of a solvent particles, which are blue color, decreased. Look, some of the particles replace it by a black color, which is, this is solvent, which is a solute. The black color is a solute. Now, because of the amount of particles of a solvent decreases, so less particles can stay to be vapor. We have less vapor of a solvent. Why? Because we have less molecule of a solvent, so we will have less vapor. Why? Because we will have less molecules number of a solvent. If we have less molecule, of course, less molecule will be vaporized. That's why if we add a solute into a pure solvent, what will happen to the vapor pressure? Lowering. More lowering. Why? Because of the particles of a pure solvent will be replaced by a solute particle. So the net amount or the total amount of the particles or of the solvent particles will be decreased by unit of the volume. Let's see how we can discuss that. Look. The vapor pressure of a solvent containing non-volatile solute, if we compare the vapor pressure of a solute that contains non-volatile solid, it means solvent plus solute. If we compare that one to a pure solvent, so what's your idea about their vapor pressure? Of course, the vapor pressure of that solute is less than the vapor pressure of a pure solvent. Why? Because of in here, I mean the solution, we have less number of a solvent particles, so less vapor become available. So less vapor pressure, we will have less vapor pressure for that solution. Look, the number of a solid particles increases in a given volume of a solution. So the portion, look, the proportion of a solvent, or I mean water mostly is a solvent, will be decreased. So what will happen if the number of water molecules decreases? Of course, less water available to be vaporized. That's why the vapor pressure decreases. Okay. Now, why vapor pressure is a colligative property? For answering this kind of question, why that thing is a colligative property? Okay, there's a general answer. Because of it depends on the concentration of a solute rather than their identity. Why that property is a colligative property? Because it depends on the concentration of a solid. It will be increased with increasing the concentration, decrease with decreasing the concentration. Now, which of the following solutions has the lowest vapor pressure? Which of them has the lowest vapor pressure? So as much as we increase the solute amount, so we will have less vapor pressure. I mean, we have more lowering in vapor pressure. Look, and here we have 0.5 molality of a glucose. Molality, this is not molar, okay? Because of, in chapter 2, we're going to talk about a pressure and temperature. That's why we should use molality. Molality, small m. Okay? So, 0.2 molar glucose, 0.02 molar glucose, or 0.5 molar glucose. And here we have most concentration. That's why we will have more lowering in vapor pressure. We have least vapor pressure. So the right answer is that. It's about vapor pressure. The second one, freezing point depression. Oh, we have mathematical problem about freezing point depression. What is the explanation of freezing point depression? Freezing point depression, as I told you, it's delta TF. F came from freezing. It's the difference between the freezing point of a pure solvent, okay, and a solution that containing non-electrolyte, non-volatile solute of the same solvent. Well, memorize this definition, but for us and for now, we only concern with the equation. Equations are very important. Look, delta TF is equal to Kf times m. Okay? The molar freezing point, Kf, the explanation is just above that slide. So delta Tf is equal to Kf times 2 molality. Kf should be given by a question, but for water, we have to know that it's minus 1.86. Minus 1.86. But for the other solvents, must be given by the question. So delta Tf is equal to Kf times molality. Delta Tf, we have another equation of delta Tf is equal to, this is according to the definition, delta Tf is equal to freezing point of the solution minus freezing point of pure solvent. So in here it means we have solvent plus solute. Solvent plus solute. Solvent plus solute. But this is freezing point of the solvent. So if the solvent is water, so the freezing point is 0 for water. Now we have two things for memorizing. Kf for water is equal to minus 1.86, and freezing point depression of water. Freezing point, we know water freezing point, pure water, freezes at 0 Celsius. Okay, so the equations is just that one and that one. I'll show you the steps of solving question about the colligative properties. So please be aware what I'm going to say. Write everything. Write everything. That's the point. That's the point. Look, what is the freezing point depression? What is the freezing point depression? Oh, freezing point depression, I remember. That's the freezing point depression, delta Tf. What is the freezing point depression of water in a solution of 70.1 gram of sucrose? Look, I'll tell you two steps of solving questions about a colligative properties. The first one, identify that the question is about boiling point or freezing point. Okay? It's about boiling point or freezing point. Well, surely it's about a freezing point. Okay, write both equations of freezing point. The first one is that delta Tf is equal to freezing point of solution minus freezing point of solvent. Okay. Freezing point of solution minus freezing point of solvent. And the second one is delta Tf is equal to Kf times to the molality. Well, teacher, now we indicated that the question is about freezing point, and we write both equations of freezing point. Okay, good job. Now, the second step, please be careful that the solute is electrolyte or non-electrolyte. It's very important because for electrolyte we have to do some further steps, but for non-electrolyte we don't have any problem. Okay, the solute is sucrose. It's non-electrolyte. Okay, solute is non-electrolyte, so we don't care about the solute. It's non-electrolyte. Well, now we have mass of solute and mass of solvent. That question asked us to calculate the freezing point depression. Oh, we have to find out the value of freezing point depression. So it will be by that question or by that equation or by that equation. It depends on the given information from the question. Well, we have gram of solute, so we have mass of solute. Look, mass of solute is equal to 70.1 gram. Okay, this is mass of solid, 70.1 gram. And we have mass of solvent also. So mass of solvent, which is water, is equal to 200 grams. Well, solvent should be in kilogram and solute should be by mole. Solvent should be in kilogram, solid should be by mole. Okay? Why? Because of we have to find out number of moles of a solute and kilogram of a solvent to find out the molality. So we should prepare molality. How we can find the molality? Molality is equal to mole per kilogram. But we don't have number of mole, teacher. Okay, it's very easy. Mole, we know that. Mole is equal to mass over molar mass. So mass is 70.1. Molar mass is equal to 342.35. So the number of mole, you see that? We have to find out molality. So in here, the number of mole is equal to 0.05 mole. Well, we have number of moles. And what about kilogram? Okay, we have gram. So we should divide by 1,000 to be 0.2 kilogram. Well, now substitute each one by their numbers and then run the equation. The number of mole is equal to 0.5 and kilogram is 0.2 kilogram. So molality is equal to, okay, just by using calculator, molality is equal to 0.05 divided by 0.2 is equal to 0.25 molal. Okay, now we have molality. Okay, teacher, how we can find out the value of a freezing point depression? Well, we have molality and we know Kf value is equal to minus 1.86. So it's very easy. We can find out delta Tf immediately by this question. So delta Tf, which is freezing point depression, is equal to minus 1.86 times 2. Molality is equal to 0.25. Oh, okay. What is the freezing point depression? So we just substituted each numbers to find out. So the answer will be minus 465. Delta Tf is equal to minus 0.465 as a freezing point depression. Okay? It will be in unit of Celsius degree. So this is in unit of Celsius degree. That's the freezing point depression. So immediately we can find out the freezing point of a solution because of the solvent freezes at 0. So delta Tf is equal to freezing point of a solution. Why? Because of freezing point of pure solvent, which is water, is 0. So they become equal values. In this question, we're going to calculate the freezing point depression, which is delta Tf. So delta Tf is equal to Kf times molality, or is equal to freezing point of a solution minus freezing point of pure solvent. So we're given, the question gives us mass of solid, which is 70.1 gram, and mass of solvent, which is 200 grams. We just turned them into kilogram and into number of mole. And after that, we've calculated the value of molality. Why? Because we should substitute molality in here to calculating delta Tf. And then delta Tf is equal to freezing point of a solution. Why? Because in here we have 0 value. The third colligative property, it is a boiling point elevation. Elevation of boiling point. Come on, okay, it's here. Boiling point elevation. So first of all, let's talk about the boiling point. There's a condition to reach the boiling point temperature. Look, boiling point of a liquid is the equilibrium between the atmospheric pressure and a vapor pressure of a liquid. Oh, it returned us to the vapor pressure. So, what does it mean, the equilibrium between vapor pressure and boiling point? Look, this is atmospheric pressure and it's vapor pressure. So, we will heat the solution until vapor pressure become equal to the atmospheric pressure. Then at that point, the solution starts to boil. So the equilibrium between vapor pressure and atmospheric pressure is the boiling point. Don't forget. What's the equilibrium between atmospheric pressure and vapor pressure? Well, it's boiling point. For example, the question says, calculate the temperature at which the vapor pressure becomes equal to the atmospheric pressure. Oh, we have to find out the boiling point. Okay? It's meaning to calculating boiling point. Well, I'll repeat to you. We have atmospheric pressure and we have vapor pressure. We should increase the temperature and the solution begins to vaporization, to be vapor. Immediately the vapor pressure will be increased until reach to the atmospheric pressure point. At that point, the solution begins to boil. Look. So the equilibrium between vapor pressure and atmospheric pressure is the boiling point. Now, look, if we have low vapor pressure, we have low vapor pressure. So we need to heating the solution more to reach the atmospheric pressure. So in that point, we have high boiling point. So low vapor pressure, we need to heat more to reach at the atmospheric pressure. So we need high temperature. Look, this range is too much. We need high temperature. So low vapor pressure, we have high boiling point. Low vapor pressure, high boiling point. Okay. So what will happen if we have high vapor pressure? So we only need a few Celsius degrees to reach at the boiling point, to reach at the atmospheric pressure. Look, high vapor pressure, we need to heat the solution a little. Okay, so high vapor pressure, less boiling point. We need to heat it more. Okay, understand that? Very good. So that's about the boiling point. If you ask it by some questions, why the boiling point of that solution is so high? Okay, the boiling point is so high because of it has low vapor pressure. Why the boiling point of that solution is very low? Because it has high vapor pressure. Okay? So what will happen if we add some solute to water? Well, adding solute into water, the vapor pressure lowers. Okay? So the boiling point elevated. Understand that? That's the point of answering the question about the boiling point. So immediately you have to talk about the vapor pressure. Why boiling point is very high? Because the vapor pressure is very low. Why boiling point is very low? Because the vapor pressure is very high. So there is a reverse proportion relationship between them. Boiling point elevation, we meant by boiling point elevation delta TB. So we have the same equations as in the case of freezing point, but we're going to change only F by B. So we have the same equations. Delta TF, in here we have delta TB is equal to KF. In here we have KB times molality. And delta TB is equal to boiling point of a solution instead of freezing point of a solution minus boiling point of a solvent instead of a freezing point of a solvent. But KB is equal to 0.51 Celsius by molality as a KB. So we should memorize this number. But for the other kind of solvents should be given by a question. About the boiling point of water, it freezes at 0 but boils at 100 degree Celsius or Celsius degree. Now we have a question about the boiling point also. Okay. Well, how to solve this question? Very good. What is the boiling point elevation? Oh, what is delta TB? Calculate delta TB. What's the boiling point elevation? Oh, teacher, the question is about the boiling point. So write both equations for the boiling point. Delta TB is equal to boiling point of solution minus boiling point of solvent. Okay, and the second equation is that delta TB is equal to Kb times 2 molality. Well, what's the boiling point elevation? We should calculate delta TB. For a solution, okay, when we dissolve 20.1 gram of non-electrolyte, okay, the second step, identify that the solute is electrolyte or not. Okay, the solid is non-electrolyte. Very good. So we don't have any further steps to do. In 400 grams of water, this is mass of solvent. So we should turn this mass into kilogram. Okay. So we have to divide 400 by 1,000 to get 0.4 kilogram. And we should calculate mole. Why mole? Because we have a plan to find out molality. We know this number, it's 0.51. And if we calculate molality, immediately we can run this equation to get the value of delta TB. How we can get the value of molality? In here, we have mass of solute and mass of solvent, so we can calculate the value of molality. But first of all, we should take the value of mole in this information. Look, mole is equal to mass over molar mass. We have mass of a solute, so the molar mass should be given by a question. Look, molar mass of a solute. When we have molar mass, immediately you have to realize that molar mass, that's useful to getting the value of number of mole from gram. So mass over molar mass is equal to 0.324 number as a number of mole. Then we can find out molality. Molality is equal to mole per kilogram. We have kilogram, it's 0.4, and we have number of mole, it's 0.324, which is 324. Molality is equal to 0.324 divided by 0.4, so molality is equal to 0.81 molar. Okay, now we have the value of molality, so just substitute the value in here. Immediately we can get the value of delta TB, but in unit of Celsius degree. Look, delta TB is equal to Kb is 0.51. Look, we have the value of Kb 0.51. Okay, and then times 2 molality. Molality is equal to 0.81. 0.81. So we can get the value of delta TB in unit of Celsius degree. Okay, it's actually there is no any difficult things in a question about a colligative properties. Just write the equations and everything will be clear. Because of, look, we have only 2 equations. We have to get the value of delta TB. We have Kb, so if we find out the value of molality, immediately we can get the value of delta TB. Well, what is the boiling point of a solution? We have delta TB. Okay, look, we find out the value of delta TB. And boiling point of a solvent is 100 Celsius degree. So just by making your subtraction and using your calculator, you can find out the value of a boiling point of a solution. Well, I don't want to talk about boiling point more because of everything is the same. Now, did you remember I told you you have to indicate that the solute is electrolyte or not? Well, let's study electrolyte and colligative properties. First of all, we have sugar as a non-electrolyte. For example, C6H12O6. When we put the sugar into water, we will get C6H12O6, but aqueous in here. It dissolves it in water. For dissolving 1 mole of electrolyte, we will get 1 mole of dissolved particles. So they're just going to be dissolved molecule. But what about electrolyte? For example, HCl. If we put some HCl into water, or KCl. KCl is ionic compound, so it is dissociate to form K plus chlorine negative. Oh, if we dissolve 1 mole electrolyte, at least we should get 2 moles of the particles. Look, 1, this is 1. So we have 2 mole of the particles. That's the difference between electrolyte solutions and non-electrolyte solutions. Why? What's the difference? For 1 mole of non-electrolyte, we get 1 mole of dissolved particles. But for 1 mole of electrolyte, we get at least we will have 2 moles of the particles in the aqueous solution, which are the ions. Well, I prefer to solve a question about the electrolyte. Okay. BaNO3 solution raises boiling point. No, that's not. What's the expected freezing point? Magnesium sulfate dissolving water. Okay, that's a very good question. Look, what's the expected freezing point depression? It means calculate delta TB. Calculate delta TB. For a solution that contains 2 mole of magnesium sulfate. Oh, that's the solute. So identify the solid is electrolyte or not. It's electrolyte, it's salt. So it's salt. Electrolyte. Oh, it's electrolyte. So we have to write the equation of the dissociation reaction of magnesium sulfate. This is magnesium sulfate, MgSO4. H2O should be right above the arrow because of this is dissociation reaction. Water does not interfere the ions, as we discussed it in a prior lecture. And SO4 negative 2. So we get 2 moles of ions. Okay. What's the matter with that number 2? We should put that number 2 in somewhere. Okay. Calculate delta TB if we dissolve 2 mole of magnesium sulfate in 1 kilogram of water. So that's very clear. We should get the value of molarity in this 2 number. Molarity is equal to mole per kilogram. So is equal to mole is 2. And kilogram is 1, so molality is equal to 2 molal. Now we have molality, so let's find out the value of delta TB. Delta TB is equal to Kb times 2 molality. Times 2 a new thing. We don't have that thing in case of non-electrolyte solute. But in here, because of the solute is electrolyte, so we should multiply by mole of ion. Mole of ions. Okay. Delta TB is equal to Kb is 0.51 times 2. Molality is 2 times 2. How many mole do we get when 1 mole of the MgSO4 dissociated? Okay, 2. So times 2. Whoa, teacher, we have 2 mole of magnesium, so we should multiply that number 2. No. This is different. This information, we have this information just to calculating molality. You have to write the dissociation reaction for 1 mole only. Okay. So we can find out the value of delta TV in unit of Celsius. So that's the relation between electrolyte and colligative properties. Okay, so for the last colligative property, which is reverse osmosis, let's explain reverse osmosis. What is reverse osmosis? Raising or increasing reverse osmosis, or reverse osmosis elevation. Well, it's the fourth colligative property. We don't have any mathematical equation in here. We just mentioning some theoretical things, and the chapter 2 will be finished. Okay. Semi-permeable membrane, osmosis, osmotic pressure. There are three new terms. We don't know what they are. Well, let's start by this picture. First of all, we have a U-tube, a glass shape. Okay, in here we will put a semi-permeable membrane. Semi-permeable membrane. What is a semi-permeable membrane? It's a membrane that allows to pass some particles through it, but preventing the others. It means we have two types of particles. One of them can pass through this membrane, but the second one cannot. So it's almost more or less like a filter. Okay. In the left side, where it doesn't matter that side or that side, but in here we have left side. In the left side, we will put a sucrose solution, an electrolyte solution. And in the right side, we have a pure water. We have a pure water. Okay. In the right side, we have a pure water. So what will happen after adding high concentration solution in here and low concentration solution in here? Well, suppose that in here we have low concentration, here we have high concentration. In here, there is a lack of water. So immediately the molecule of water begins to pass. The molecule of water begins to pass through the semi-permeable membrane. Okay? By what? By osmosis. So what's the osmosis? Passing the solvent molecules through the membrane. Passing the solvent molecules through the membrane. In where to where? In a low concentrated solution to a high concentrated solution. Okay? So what will happen if a water molecule passes through this membrane? It will receive a water. So immediately there will be a raise of volume because of it reaches more water molecules. But what will happen? Because of here, it makes a pressure. So that pressure prevented this volume to be raised anymore. So the volume, the raising level of that aqueous solution will be stopped when we have enough pressure in here. This pressure called osmotic pressure. What's the osmotic pressure? It's the pressure to stopping the osmosis, to stopping the level of the solution from raising. Okay? So at that point, the amount of water that enter to the high concentration is equal to the amount of water that exists from the high concentration. Why? To keep this level of a solution constant. So water molecule begins to osmosis, passing through the membrane, the level will be raised. That's why. So what is the condition of a reverse osmosis pressure? What's the condition of the osmosis? What is the condition of the osmosis? What will happen if we remove this membrane? Immediately both will be mixed. So the first one is the semi-permeable membrane. Okay, so what will happen if we have equal concentration? Okay, If you have equal concentration, so there will not be any water passage through this membrane. So the second one is the two different concentration. So what's the condition of the osmosis pressure? What is the condition of osmotic pressure? The first one, semi-permeable membrane. The second one, two different concentration solutions. Okay, so that is the last thing that I explained about the chapter 2. تاوانی داهاتوو لە بەندی سێم ئینشاءڵڵا پێتان شاد دەبمەوە خواتان لەگەڵ.